What if every single distance ever measured in space is wrong? Not slightly off, not rounded for convenience, but fundamentally flawed at the deepest level of reality. The distance between Earth and the Sun, the size of the Milky Way, the observable universe itself. What if none of these measurements describe something real? What if distance, the most basic property of space, does not actually exist? To understand why, we need to start with something deceptively simple. A light year. Most people think of a light year as a unit of distance. And technically, it is. It tells us how far light travels in 1 year, roughly 9.46 trillion kilometers, but here's the problem. A light year is not really measuring space, it is measuring time. When astronomers say the Andromeda galaxy is 2.5 million light-years away, what they really mean is that the light arriving from Andromeda tonight left that galaxy 2.5 million years ago. We are not seeing Andromeda as it is now, we are seeing a ghost. A snapshot of a galaxy that may have already changed in ways we cannot know. And during those 2.5 million years, the universe has been expanding. The space between us and Andromeda has been stretching. So the galaxy is no longer 2.5 million light-years away. It is further. How much further? That depends on which definition of distance you use. And this is where the trouble begins. In 1905, Albert Einstein published his theory of special relativity. And buried within it was a deeply unsettling idea. Distance is not the same for everyone. Imagine a ruler floating in space. To you, standing still, it measures exactly 1 meter. But now imagine that ruler is moving past you at 90% the speed of light. According to special relativity, that ruler would appear to be only about 44 centimeters long. Not because it has been compressed, not because your eyes are tricking you. The ruler genuinely is shorter in your frame of reference. This effect is called length contraction. And it means that two observers moving at different speeds will measure completely different distances between the same two objects. Neither is wrong. Both measurements are equally valid. There is no universal, objective distance between any two points in the universe. It depends entirely on how fast you are moving. Now take this to its extreme. A photon, a particle of light, travels at the speed of light by definition. And from the photon's perspective, length contraction is total. The distance between any two points in the universe, no matter how far apart, contracts to zero. To a photon leaving a star in the Andromeda galaxy, the journey to your eye takes no time and covers no distance. It departs and arrives in the same instant. For light itself, space does not exist. But Einstein was not finished dismantling our understanding of distance. 10 years later, in 1915, he published general relativity, and this theory went even further. It showed that massive objects do not just exist within space, they warp it. The sun, for instance, bends the space around it like a heavy ball resting on a rubber sheet. This means that a straight line near the sun is not actually straight, it curves. And if the path through space curves, then the distance between 2 points is no longer fixed. It depends on what lies between them. Near a neutron star, distances stretch. Near a black hole, they become almost meaningless. At the event horizon of a black hole, space is curved so severely that the distance to the center becomes, in a sense, infinite, even though the black hole has a finite size as seen from the outside. An observer falling in would cross the horizon in finite time. But the geometry of space itself has been so distorted that our usual concept of distance simply breaks down. General relativity does not just bend distance. In extreme cases, it destroys the very idea of it. And yet, all of this is special relativity. General relativity still assumes that space is a smooth, continuous fabric. Stretch it, curve it, compress it, but it remains something. A stage on which the universe performs. But what if space itself is not fundamental? What if it is an illusion, emerging from something deeper? This is where quantum mechanics enters the picture. And it brings with it the strangest phenomenon in all of physics, quantum entanglement. When two particles become entangled, they share a connection that transcends space. Measure one, and the other responds instantly, regardless of the distance between them. This is not information traveling faster than light, it is something more disturbing. The two particles behave as though the space between them does not matter. As though distance, for them, is irrelevant. Einstein called this spooky action at a distance, and he spent years trying to prove it was wrong. He failed. Experiment after experiment has confirmed that entanglement is real. And what it suggests is profound. Two entangled particles on opposite sides of the universe are, in a quantum mechanical sense, closer to each other than two unentangled particles sitting side by side. In the 1990s, physicists began to formalize this idea. The holographic principle, developed by Gerard T. Hooft and Leonard Susskind, proposed something remarkable. All the information contained within a three-dimensional volume of space can be encoded on its two-dimensional boundary. Think about what that means: the depth you perceive, the sense of three-dimensional space stretching out in front of you. It may be a projection, an emergent phenomenon arising from information encoded on a distant surface. If the holographic principle is correct, then the interior distance you experience is not fundamental. It is constructed. It emerges from the relationships between quantum bits of information on the boundary. This idea was made mathematically precise by Juan Maldacena in 1997 through a framework known as the ADS-ECFT correspondence. In this framework, a universe with gravity and three spatial dimensions is completely equivalent to a quantum system living on its lower dimensional boundary, a system with no gravity and no concept of depth. Distance in the higher dimensional space arises directly from patterns of entanglement in the lower dimensional system. More entanglement between two regions means they are closer together in the emergent space. Less entanglement means they are further apart. Distance is not a property of the universe. It is a consequence of how quantum information is organized. In 2006, physicist Mark van Raamsdonk pushed this further with a striking thought experiment. He asked, what happens if you take a quantum system described by ADS-ECFT and gradually reduce the entanglement between two halves? The answer was extraordinary. As entanglement decreases, the corresponding region of space begins to pinch and stretch. Reduce it to zero, and the space tears completely in two. To disconnected universes with no bridge between them. Entanglement was literally holding space together. Without it, there is no space, no distance, nothing. This leads to one of the most profound equations in modern physics. ER equals EPR, proposed by Maldacena and Susskind in 2013, it suggests that every pair of entangled particles is connected by a tiny wormhole, a bridge through space-time. Not a wormhole large enough to travel through, but a fundamental link in the quantum fabric that gives rise to what we call distance. If A equals EPR is correct, then every connection in space, every distance between every pair of points, is ultimately a manifestation of quantum entanglement. But there is one final layer, one more reason to believe that distance is not real. Loop quantum gravity, one of the leading candidates for a theory of quantum gravity, predicts that space is not continuous. It is made of discrete, indivisible units, tiny loops of gravitational field woven together into a structure called a spin network. The smallest meaningful length in this framework is the Planck length, roughly 1.6 times 10 to the minus 35 meters. Below this scale, the concept of distance ceases to exist, not because we cannot measure it, but because there is nothing there to measure. Space itself is granular, pixelated, and at the smallest scales, the smooth, continuous distance we experience is revealed to be an approximation. A convenient fiction. So where does this leave us? Every tool physics has developed to examine distance has returned the same verdict. Cosmology tells us distance changes as the universe expands. Special relativity tells us distance depends on how fast you move. General relativity tells us distance warps in the presence of mass and energy. Quantum entanglement suggests distance is a byproduct of information. And quantum gravity hints that space itself may be discrete, with distance emerging only at scales far larger than the fundamental structure of reality. Look up at the night sky. The stars appear scattered across a vast, three-dimensional void. Andromeda seems impossibly far away. The edge of the observable universe feels like the ultimate boundary. But every one of those distances, every light year, every parsec, every billion kilometers, may be nothing more than an emergent property of a deeper quantum reality. A reality in which there is no space, no separation, no distance. Only information, only entanglement, only the quantum fabric from which the illusion of distance is woven. The universe is not a vast, empty expanse with objects scattered across it it is a quantum system. And spacey, with all its apparent distances, is simply what that system looks like from the inside.